Math 1332, Chapter 2, Set Theory, Section 5, Infinite Sets, Video 2, General Term of an Arithmetic Sequence. This still involves infinite sets, but we're going to be looking at some specific infinite sets called arithmetic sequences. By the way, the word arithmetic looks like the word arithmetic because it's spelled the same way. But when it's pronounced arithmetic, it's an adjective. In this case, an arithmetic sequence. When it's pronounced arithmetic, it's a noun, as in the subject of studying the mathematics of numbers. So let's start with the definition of a sequence. Now, everybody kind of knows what a sequence is, but it does have a formal definition. This is not the formal definition, by the way. A sequence is a list of numbers in a particular order. There doesn't have to be any reason for that order. In case you're wondering what the specific definition of a sequence is the range of a function whose domain is the natural numbers, but we're not going to get into the definitions of all those words. So for our purposes, a sequence is just a list of numbers, and it doesn't have to be in any particular order. So for example, we could say, and I'll be honest with you, they don't even have to be numbers, but for our purposes, we'll leave them as numbers. Let's say I put the number 3 followed by the number 1, followed by the number 4, followed by the number 1, followed by the number 5, followed by the number 9, and we'll ... And it looks like I'm just writing digits in some random order. I'm not. There's a method behind my madness, but there doesn't have to be any reason they're in a particular order. Now, it is worth noting that if I switch the order of any two of them, like the first two, but leave the rest alone, this is considered a different sequence, because a sequence does have an order to it, meaning that if you switch it up, it's a different order, so it's a different sequence. By the way, if you're wondering what was the method behind my madness, those are the digits of pi, or at least the first 6 digits of pi. So what is an arithmetic sequence? Well, an arithmetic sequence is a sequence where the difference in consecutive terms is constant. Let me explain what I mean by difference in consecutive terms. If you take 2 consecutive terms and subtract them, so 1 minus 3, it's always the second minus the first. 1 minus 3 is -2. But then you take a different pair like this one and do 5 minus 1, you get 4. You can think of the subtraction problem as answering the question, what do I have to add to get from one number to the next? In this case, I would have to add -2 to get from 3 to 1. What would I have to add to get from 1 to 4? Well, 4 minus 1 is 3. I would have to add 3. What would I have to add to get from 4 to 1? It's kind of tricky because it goes down, but anytime you add and the result goes down, it's because you added a negative. I would have to add -3. And then I would have to add 4, and then I would have to add 4 again. In an arithmetic sequence, the difference is the same in every pair of consecutive terms. So neither of the sequences that I have listed up there are arithmetic. However, let's say I have the following sequence: 1, 4, 7. I'm establishing a pattern. Can you predict the next number? I'll give you a hint. I'm building an arithmetic sequence, which means the difference is the same in every pair of consecutive numbers. If you said 10, you were correct. What would the next one be? 13. Why? Because the consecutive difference between any two numbers is 3. 4 minus 1 is 3. Remember, it's always the second minus the first. 7 minus 4 is 3. 10 minus 7 is 3. 13 minus 10 is 3. So that's what makes a sequence arithmetic. When I subtract one number minus the one in front of it, I get the same answer every time. So let's consider an arithmetic sequence. And I do want to point out that this is an arithmetic sequence. The set starting with 2, and then 9, and then 16, and then 23 in that order. How can you tell it's arithmetic? Well, you ask yourself, what do I get when I subtract one number minus the number in front of it? Or equivalently, what do I add to one number to get the next number? Either way that you look at it, to get from 2 to 9, I would have to add 7. To get from 9 to 16, I would have to add 7. To get from 16 to 23, I would also have to add 7. So it looks like this is what some people would call a +7 pattern. All right, so let's see if we can figure out some terms in the sequence, starting with the 10th term. I'm going to go ahead and write it again. 2, 9, 16, 23. All right, we're already at the fourth term, so we've only got 6 to go. And we know how the sequence progresses by adding 7. So all we have to do to get to the 10th term is keep adding 7. What's 27 plus, what's 23 plus 7? 30. What's 30 plus 7? 37. What's 37 plus 7? 44. And don't feel like you can't use a calculator to do these. The addition here is pretty simple and you should be able to do it without a calculator, but I'm not testing you on your arithmetic and algebra skills, so feel free to use a calculator for any numerical calculations. 44 plus 7 is 51. Wait, where are we? 1, 2, 3, 4, 5, 6, 7, 8. 2 more. 51 plus 7 is 58. And finally, add 7 one more time. 58 plus 7 is 65. So it looks like the 10th term is 65. Okay, well, that's not too bad. That's just picking up on a pattern and continuing it until you get to the position in the sequence that you want. In this case, the position was the 10th position. Look at the next question. What is the 50th term in the sequence? Now, could we do the same thing we did before, which was keep adding until we get there? We could. But I think this one makes you want to not keep adding 7 until you get to the 50th position. I think this one kind of motivates you to ask, is there a quicker way to get to the 50th term in the sequence without having to add 7 a bunch of times? Well, how many times will we have to add 7 to get there? 50 times? Not really. In order to see how many times we would have to add 7 to get to the 50th term, let's go back to the previous example. How many times did we add 7 to get to the 10th term? And I should be specific to get to the 10th term from the first term. So let's go back up here and write in our 7s all the way back to the first term. So to get to the 10th term, how many 7s do you have to add from the beginning? If you said 10, count again. 1, 2, 3, 4, 5, 6, 7, 8, 9. We only had to add 7 9 times. So why do we not have to add it 10 times? Because when we add it the first time, we're already at the first term and it takes us to the second. We don't have to add 7 to get to the first term. We're already at the first term. So our first number added takes us to the second term. The second 7 added takes us to the third term, so on and so on and so forth. This 9th 7 added got us to the 10th term. So I'll ask again, to get to the 50th term, how many 7s do you think we're going to have to add? It's not 50, it's 49. Because we don't need that 50th one because we already start in the first position. Adding the first term already takes us to the second position. Adding the first 7 takes us to the second position. Adding the second 7 gets us to the third position. Adding the third 7 gets us to the fourth position. So to get to the 50th position, we will only have to add 7 49 times. So does that mean we're going to add 7 49 times? Well, not really, because there's some arithmetic that can help us with this. We need to start with the first term, which was 2, and add the difference, which was 7, a total of 49 times. Let me do a couple of things. Let me widen this text box and then get out of it. There we go. So is there a more efficient way to add 7 49 times? And I left out the S from the word times. That's going to bother me. There we go. All right, so again, is there a way to add 7 to something 49 times without going plus 7, plus 7, plus 7, plus 7, plus 7? The answer is yes, because adding 7 49 times is the same as 49 times 7. In other words, to get the 50th term, we need to start with the first one and add 7 49 times. So 7 times 49. Now, there is an order of operations issue here. Please excuse my dear Aunt Sally if you know what that means. If you don't, it simply means in an arithmetic problem like this, you have to multiply before you add. So if we multiply 7 times 49, I believe that gives us 343. And then if we add that, we get 345. And now I know which number is in the 50th position without having to count out all the first 50 terms. In case you haven't figured it out, we're going to make this a little bit generic by trying to set up a formula for this particular case and then turn it into a formula for all cases. Recall, to get to the 10th term, we added the difference 9 times. To get to the 50th term, we added the difference 49 times. So how do we get to a general term? In other words, the nth term. Think of it this way. If we had the natural numbers here, 1, 2, 3, 4, ... and we had an n representing some generic position. And I know earlier I said n stands for cardinality, but I'm going to go ahead and use it here to represent a general position in the sequence. If we try to put our arithmetic sequence in one-to-one correspondence, so it started with 2, and then 9, and then 16, and then 23. I think it's pretty transparent that we can put both of these sets in one-to-one correspondence. But the question is, what would happen in general? In other words, the question we're trying to answer is, what do we do to the numbers 1, 2, 3, 4 to get the numbers 2, 9, 16, 23? Because if we can answer that, then we can determine any element in any position based on its position number. For example, we figured out that the number in the 50th position, the 50th term, was 345 by doing something to the number 50, not by taking 2 and adding 7 until we got to the 50th position, although we kind of did that. So how can we do this? Well, let's think about what we did for 50. What do we do with 50 to get 345? Well, we started with the first term. And then we added something to it. We added the product of the difference, and not the position number, but 1 less than the position number. So let's see if we can replicate that down here, and then on the next page, we'll turn it into a nice formula where you don't have to figure anything out. You just got to follow protocol. All right, so how did we get to the 50th term? We started with the first term, which was 2. And to that, we added a bunch of 7s. But how did we know how many 7s to add? Do we add 57s? No, we added 1 less than that. We added 49 7s. So for the general term, the nth term, do we add this many 7s? No, we add 1 less than that. That's how many 7s we have. And that would be our general term in this particular instance. Now, could we clean that up? Actually, yeah, we could. Should you? I think the homework's going to want you to. So just a real quick how to clean this up. You would have to invoke the distributive property, which means you have to multiply everything by 7. So 2 plus 7n, and then 7 times -1 is -7. And then upon doing that, it will expose some like terms that you can combine to a -7. So if we can combine those, leave the 7 in alone, 2 minus 7 is -5. So this would actually be, in my opinion, the best answer for what is the nth term. What is the general term? The general term is 7n minus 5, and I don't like that highlighting. Let's use a different color. There we go. Is it the correct answer? Well, we could check it real quick. How? We know what the first 4 terms are. If n equals 1, if n equals 1, then what would 7n minus 5 equal? 7 times 1 minus 5, but that's 7 minus 5, which is 2. So that's the correct value. What if n equals 2? Then we would have 7 times 2 minus 5. That's 14 minus 5, which is 9, so that would be correct. Now we could check all of them, but I promise you it's the correct term. We'll just take the third one. We get 7 times 3 minus 5. That's 21 minus 5, which is 16. So we do have the correct general term, the nth term, if you will. And either one would be correct. The one down here, 2 plus 7 times n minus 1, or the cleaned up version where we distribute to get rid of the parentheses and then combine like terms. So how do we do this? Excuse me. How do we do this in general? Well, it's actually not that hard. We just have to represent things generically. And to represent an arithmetic sequence generically, you need two pieces of information. What does it start with, and what's the common difference? In this example, it started with 2. And if you notice, I use a capital A to represent the first number. And the common difference was 7, meaning what happens when you take one term and subtract the one prior to it, or equivalently, what do you add to one term to get the next one? So if we're going to make this generic, we need to remove all specificity from this problem, and this problem is a specific first term and a specific difference. But what if we have a generic first term of A and a generic difference of D? But what's the general term in the nth position? Well, it would work the exact same way as before. We would take the first term and add to it the difference times not the position we're in, but one less than that. Because remember, that first addition takes us to the second term because we started the first term. So here's your formula. Now, could you distribute and combine like terms? You could, but because this has 3 variables in it, I don't see an advantage to it. I would only distribute and combine like terms when you have a specific value for the first term, A, and a specific value for the difference, D. Let's take a look at an example. Find the general term for the arithmetic sequence 23, 20, 17, 14, and so on. Now, you might be thinking, wait a minute, this one doesn't look the same because the numbers are going down instead of going up. But remember, what makes a sequence arithmetic is that the difference between one term and the term prior to it is always the same. For example, if we did 20 minus 23, the second term minus the first term, that's -3. If we do the next one, 17 minus 20, that is also -3. And in fact, if we do 14 minus 17, remember it's a number minus the one in front of it, then we would get -3. Does it matter that the difference is -3? No. All that matters is that the difference is the same anytime I take one term and subtract the one prior to it. So let's get rid of all this over here. And let's make a note that the first term which I called capital A generically is A equals 23. And the difference is D equals -3. Negative because the sequence is going down instead of going up. Then the nth term, the general term, if you will. And by the way, nth is a legitimate word, NTH. You can play it in Words with Friends or any other word game. Oops, I'm writing general. The nth term is, let's go back, let's look at our formula up here. It's the first term, so 23, plus the difference, which is -3, times n minus 1. All right, now I am going to ask you to distribute the difference across the parentheses and combine like terms. Now be very careful when the difference is negative. Well, let's bring our 23 first. -3 times n is -3n. And -3 times -1, negative times negative is positive, and 3 times 1 is 3. And now we have two like terms to combine. We have this 23 and this +3. And so if we write it with the term with the n first, we have -3n. 23 plus 3 is 26. And that would be our final answer. If the negative threw you off, don't let it bother you too much. Just remember your negative rules for adding and multiplying, and you should be okay. Let's try another one. Oh no, fractions. Everybody run and scream. Ah. But look a little more closely at these fractions. They all have a common denominator. And since we're going to be adding and subtracting mostly, That's good because to add and subtract fractions, you first get a common denominator, which all these have, and then you just do the addition or subtraction in the numerator. But first, let's verify that it's an arithmetic sequence by subtracting consecutive terms. If we do 5/7 minus 1/7, the rule for subtracting fractions and adding fractions is get a common denominator and then do the math to the numerators. And if you, for some reason, you have trouble seeing this, I'm going to show you something that may open your eyes to fractions. The denominators are really units of measures, like feet or inches or pounds. It's just they're written numerically. You could write them in words, 5/7 minus 1/7. Now, you don't have to know what a seventh is, but you should know that if you have 5 of them and take away 1 of them, you have 4 of them. I don't advocate subtracting fractions by first changing their denominators to words, but it really opens up a lot of people's eyes as to why you add and subtract fractions the way that you do, because the denominators are really just units of measurements. Like imagine cutting a pizza into 7 slices, which would be ridiculous because 7's odd. But if you did, and you had 5 slices and took away 1 slice, you would have 4 slices, but the type of slice would remain the same. They would all be 7s. What changes is how many of them that you have. Now, I'm not going to do that every time I subtract fractions, but it does kind of expose why you have to get common denominators. But we were verifying that this was an arithmetic sequence by subtracting consecutive terms, 5/7 minus 1/7. Now let's look at 9/7 minus 5/7. That's still 4/7, because if I didn't tell you that it was an arithmetic sequence, you would have to verify it first in order to do what we're going to do. So we verified that the common difference is 4/7, and the first term is exactly that. It's the first term, it's 1/7. So what's the nth term? I'm going to have to get rid of the red stuff over here. 1 second. There we go. All right, so the nth term is going to be, let's go back and look at our formula. It's right here. Our nth term is going to be the first term, which is 1/7, plus the difference, 4/7, times n minus 1. Again, don't let the fractions intimidate you here. If we distribute the 4/7, we get 1/7 plus 4/7 times n. That's all we can do there. And for the second half of the distribution, positive times negative is negative, and 4/7 times 1 is 4/7. And now we have 2 like terms to combine, 1/7 minus 4/7, but those already have a common denominator. Let's write the term with the n first, 4/7 n. For 1/7 minus 4/7, they already have a common denominator. So we just have to subtract on the top. 1 minus 4 is negative 3. So we have 4/7 n minus 3/7, and that would be our final answer to this problem. And now, if I wanted to, I could ask you any position in the sequence. Like I could ask you, what is the 100th position in the sequence? Well, since I opened up that can of worms, let's go ahead and do it. 100th term would be 4/7 times 100 minus 3/7. The rule for multiplying fractions is you multiply numerators and denominators. The 100 is a fraction if we put it over a 1. And so multiplying on the top gives us 400, and on the bottom gives us 7. That's good. We still have a common denominator. 400 minus 3 is 397, which is not reducible, and that would be our 100th term. So that's what the general term can do. It can give you any position in the sequence. All right, I want to close this video, which has probably been going longer than I wanted to, with a warning that not all sequences are arithmetic. Remember, what makes a sequence arithmetic is the difference in any 2 consecutive terms is always the same. But not all sequences are like that. For example, let's say I ask you to find the general term for the sequence 1, 4, 9, and 16, so on and so forth. If you were to check the common differences, if you were to check the differences, the first difference is 3, but the second difference is 5, and the next difference is 7. And you might be going, ooh, there's a pattern there, and you're right. but it's not the same difference each time, which means it's not an arithmetic sequence, which means we could not do this formula on it. Does that mean there's not a way to get the general term? Well, there is a way in different types of sequences. Sometimes it's just a case of observation. And remember, to get the general term, all we're really asking is if we park the natural numbers on top, what are we doing to the natural numbers to get the numbers below? 1, 4, 9, 16, etc. And this one might be transparent now that I've written the natural numbers above it. What do you do to 1 to get 1? But the same thing that turns 2 into 4, that turns 3 into 9, that turns 4 into 16. You might recognize that these numbers down here are all perfect squares. 1 squared, 2 squared, 3 squared, 4 squared. So if what I'm doing to a term is squaring it, then that means that the nth term would be n squared. Now that one might be fairly transparent, it might not be. Or this one. Find the general term for the sequence 2, 4, 8, 16. Now, again, if you start looking for patterns, you may find one, but it's not an additive pattern. And to clarify the difference, I'm going to go back here and put plus in front of all these. I'm not going to go back in all the previous ones and write pluses or minuses because the pattern here is not additive at all. Yeah, you add 2, you add 4, you add 8. So it's almost like you're adding something to itself, but that's the same thing as doubling it. Times 2, times 2, times 2. This is a multiplicative pattern. Such a sequence is called a geometric sequence. What is the nth term? Well, let's set up the natural numbers. And let's set up the sequence below it, 2, 4, 8. I left out 4 up there. What do you do to 1 to get 2? But the same thing turns 2 into 4, turns 3 into 8, and turns 4 into 16. It may not be obvious unless you've recently done the homework about finding the number of subsets of a set, which was 2 to the nth power. And you may recognize that these are powers of 2, that this is 2 to the first power, this is 2 to the second power, this is 2 to the third power, 16 is 2 to the fourth power. And at that point, you realize that the number on top is just the power that you put on 2, which means that the nth term would be 2 to the nth power. But my point was not all sequences are arithmetic. I think in your homework, I'm going to try to make sure they're all arithmetic. I may throw one non-arithmetic sequence in there to see if you can pick up on the pattern.